In this video, we're going to continue to work on zeros of polynomial functions. So let's talk about the rational zero theorem first. If you have a polynomial function that has integer coefficients, then every rational zero of the polynomial function has the form of factors of a0 divided by factors of a of n. Now, let's figure out where a0 is. A0 is right there. Well, what is that? Since it doesn't have any variables, that's the constant. So it's factors of the constant. Now, where's a of n? Well, a of n is right here. Well, not only is that a coefficient, that is the leading coefficient. Okay. I'm going to abbreviate that LC. All right, so I want to list all possible rational zeros for this polynomial function equation. Okay. So, first thing I would like to do, let's write out factors of constant. Well, the constant here is 10 divided by factors of leading coefficient, which is 6. So, factors of 10 and factors of 6 are 1, 2, 3, and 6. So then from there, I need to be able to list all of these out as such. So what I would recommend is start with the 1 in the numerator and divide it by every single number in the denominator. So in this case, that would be what? 1 over 1, 1 over 2, 1 over 3, 1 over 6. Now, I'm going to do the same thing with 2 now in the numerator. 2 divided by 1. 2 divided by 2, that's 1, we already have. 2 divided by 3. 2 divided by 6, that's 1/3, we already have. Now, let's go to the 5. 5 divided by 1. 5 divided by 2. 5 divided by 3. And 5 divided by 6. Now, let's go to 10. 10 divided by 1. 10 divided by 2, that's 5, we already got. 10 divided by 3. And 10 divided by 6 is 5/3, we already have that. These are the only possible rational zeros. Now, we know the degree of this polynomial function equation is 3, so we know the maximum number of solutions it's going to have is 3. So not all of them are going to be solutions, but if any of them are, you're going to find them somewhere in this list. Okay? So note, not all of these numbers in the list will be a zero of the function, but every rational zero of the polynomial function will appear somewhere in that list. Okay, so now I want to list out all the possible rational zeros. Then use that list to write the factor of p of x as a product of linear and irreducible quadratic factors, then determine the zeros. All right, so let's start with writing out all of the possible rational zeros. So again, that is going to be what? Factors of the constant, which again, I don't care about the negative, just put 6. Factors of leading coefficient, which is 1. Okay, factors of 6, 1, 2, 3, and 6. Factors of 1, that's really simple, so I can simplify. These are the only possible rational zeros for this polynomial function. Okay, so let's try one. Let's try -1. Okay, so write out. Now remember, because I'm trying to find factors I want to divide. Again, 2 options, either long or synthetic division. I'm choosing to use synthetic division here. Okay. All right, so let's go through this. Oh, that's nice. That means x plus 1 is a factor. And we also know -1 is a 0. Okay. So what am I left with? I'm left with x cubed minus 3x squared plus 2x minus 6. Remember, I want it to be a smaller degree polynomial function, so eventually I could use other techniques other than this long or synthetic division. Now, I'm going to check to see if this can factor by grouping. So, what can I factor out of the first two terms? That's an x squared. I'm left with x minus 3. What can I factor from the last two terms? Oh, that's a 2. I'm left with x minus 3. Ooh, now that's nice. That means I can put this together then as x squared plus 2 times times x minus 3. So p of x can be written as x plus 1, x minus 3, I'll put that first, and then x squared plus 2. Now, my zeros. Two of these I can tell very quickly. If x plus 1 is a factor, then the 0 is negative 1. If x minus 3 is the factor, we know the 0 is 3. Now, I've got to do a little bit of work for x squared plus 2, so let's do that here. Set this factor equal to 0, subtract the 2, and then take the square root of both sides. Now remember, I need to pull out an imaginary unit of I. Make sure it's outside the square root. So my other two solutions are plus or minus the square root of 2 times I. Again, notice the degree is 4. I have 4 zeros. And in this particular case, they are unique. And notice, one of the complex solutions and its conjugate are both solutions for this. All right, the other thing I want to talk about in this video is what is called Descartes' rule of signs. Okay? Descartes' rule of signs lets me know the possible and the type of solutions that you may or may not have. Okay? So let's take a look. So suppose you have a polynomial function equation. The number of positive real zeros of the polynomial is equal to the number of sign changes of the original polynomial function, or less than that number by an even integer. Okay? And the number of negative real zeros of the polynomial is equal to the number of sign changes of p of negative x, or less than by an even number. All right, so let's take a look at an example for this. So suppose you have this polynomial function equation. We would like to be able to find the possible number of positive and negative real zeros and complex roots. So let's start with possible positive reals. Now, remember, it's the number of consecutive sign changes. Well, you're going from a positive to a negative, that's 1. Negative to a positive, that's 2. Positive to a positive doesn't count. Positive to a negative, that is 3. And a negative to a positive, that is 4. So I can have 4. But notice, I can subtract it by an even number. Well, if I take 4 minus 2, that is 2. Then I can take 2 minus 2, which is 0. So I'm going to stop either when my number is 0, or if I subtract 2, I get a negative number. It doesn't make sense to talk about the possible positive reals and it being a negative number. So in other words, I could have 4, I could have 2, or I could have 0 possible positive reals. And again, I don't know that until I actually solve this polynomial function equation. All right, let's talk about possible negative reals. Okay. Now, I'm going to take a look at p of negative x. So every time I see an x, I'm going to replace it with negative x, and then I'm going to simplify. Okay, so a negative taken to the 5th power is negative. This is still going to be negative, and that's going to be negative, positive, positive, and this constant will remain positive. Now, again, you are going to count for consecutive sign changes. So, negative to a negative can't do. Negative to a negative doesn't help. Negative to a positive, that's 1. And since the rest of the signs are positive, I only have one sign change. So there's only one possible negative real. Okay? Now, what I would like to do is to set up a table for all my different possibilities. So I'm going to draw this. Okay. going to call this possible positive reals, possible negative reals, so I don't have enough room, and complex. Okay. So let me do this. Now, very important to know what the degree of this polynomial function equation is going to be. Well, since the degree is 5, the most number of unique solutions I can have is 5. Okay? So let's go to the possible positive reals. I could be 4, 2, or 0. Well, let's start with 4. Okay? Okay. That means I could have one possible negative real. That's not going to change. Well, 4 plus 1 is 5. We know the total degree is 5. 5 minus 5, that's 0. So going across, it should add up to equal 5. Because again, I should have at most 5 solutions. Okay, now let's go to the 2. Still, my only option here is 1. And then that leaves me 2 plus 1 is 3. Subtract 3 from 5. That leaves me with 2 complex solutions. And again, 2 plus 1 plus 2 is equal to 5. The most number of unique solutions I can have here is 5. My other scenarios, I could have 0 possible positive reals, still 1 possible negative real, and that would leave me with 4 complex solutions. Okay. And remember, your complex solutions are always going to be in pairs, the original and its conjugate, the original and its conjugate. The last thing I would like to discuss is upper and lower bounds. So let f of x be a polynomial with real coefficients and a positive leading coefficient. Suppose f of x is divided by x minus c using synthetic, or you could use long division. If c is greater than 0 and each number in the bottom row is either positive or 0, c is an upper bound for the real zeros of f. If c is less than 0 and the numbers in the bottom row are alternatively positive and negative, 0 entries can count as either positive or negative, c is a lower bound for the real zeros of f. Okay. So what I have done is I wrote an example of each for us to take a look at. Is x plus 5 a factor of that polynomial function equation? Well, if I'm going to check x plus 5, obviously I will plug in negative 5. And again, notice in this particular case, c is less than 0 in the box, and your values are alternating, positive, negative, positive. This is telling me negative 5 is a lower bound. Try a higher number. Try negative 1. Try 1. Try 5. For the other one, x minus 8, a factor of that polynomial function equation. Well, again, plugging in 8. Now notice, every single value is positive, okay? And we know the c value is greater than 0. That, by definition, then, makes 8 an upper bound. We want to try a lower number. Maybe 4, maybe 2, maybe 1, maybe negative 2, maybe negative 4. Okay? These techniques should help us determine or help us find zeros for polynomial functions.